Okay, just a reminder for this, if you're needing some guidance on how to access this information, the documents, the resources, please remember to go into the link that I have shared with you multiple times, usually under every video or maybe in several messages, that gets you to the Earth Science Parent Portal, which gives you access to all these documents. Please make sure that you navigate either to the English or the Chinese and access the number 9 folder, which is climate. Within climate, make sure that you're accessing the notes here, and you can scroll through to see the notes in color, okay? And if you need to then find more information regarding the guided independent practice questions, you can click them here. And if you need to have any information for access points, I have an access point folder that I'm developing now too. So a few of these things you're seeing already, but at the time of making this video, that's when I was making these decisions to reorganize. All right, so we're going to be using the notes along with the climate change guided independent practice questions. So please make sure that you have both of those documents available for yourself. Okay? So what we have to talk about here is how we have different processes on the planet that will impact the climate. And one of those things we have to talk about are volcanoes. Volcanoes have massive eruptions. They send tons of dust and gas into the air. Some volcanoes are larger than others. We've had prehistoric supervolcanic events that have blocked out a vast portion of the atmosphere. We also have smaller volcanoes than supervolcanoes that erupt, like the ones that are in Iceland. We might have ones that are in Indonesia that erupt and they send ash and dust. And this year we saw one in Indonesia that erupted and was sending a lot of ash and dust into the air. Well, this is not the same as water vapor, but it still behaves like water vapor in that it's going to block the solar radiation. So during times of having a vast amount of aerosols like volcanic ash in the air, you're going to cause there to be a darkening or a blocking aspect to the atmosphere, reduce temperatures that are underneath that area. So volcanic eruptions do impact the weather, they do impact climate. Now, a word that's new, a new word that relates to the reflection of light and energy away from our ground would be albedo. So some surfaces have higher albedos than others. We can refer back to radiation in our transfer of energy, video and notes, that albedo is related to things like a white painted roof, which is going to reflect sunlight more, or the white tops of clouds are going to have more reflective property than a black top or a parking lot or a non-light colored rooftop. Okay? So let's continue talking about other aspects of climate and how it may change. So one of the things that you're going to be studying probably for years to come, and I'm sure there's going to be a large amount of attention continually put onto climate change and the potential for our climate on this planet to alter due to gases that may be related and associated to the increased temperatures that we may be seeing on average over a long period of time. So two of those gases that are very important to understand are carbon dioxide and methane. A third one, which is already here, well, all of these are already here, but another one that does additionally add to climate change would be water vapor in the air. So all three of these gases act like a layer of blankets on our planet that helps hold in heat. And let's start by saying that these are not inherently bad by themselves or originally. We do need these elements, these molecules in the air to create the environment we currently have. If these were missing from the atmosphere, we would not have a hospitable environment here at the surface for us to live in. Our concern is if we add too much of this to the atmosphere, will we get too much of a change too quickly that it will alter the environment we are living in for it to be less suitable for us to live in and for other organisms to live in. So with the addition of these, we may see in the future large temperature rises. We may see alterations in our climate that may or may not result in larger storms. It may or may not result in much higher sea level. So we have to study these and continue to build more complete simulations to determine what this means based on climate models. So how does the greenhouse effect work? Greenhouse effect? Oh, that's right, the greenhouse effect. These are greenhouse gases. If you've ever seen a greenhouse or you've ever been to maybe the, trying to think now, the botanical gardens, there you go, the botanical gardens in the Bronx, you have these large greenhouses that are going to allow light to pass through the glass, and usually that's visible light, ultraviolet light, comes into the greenhouse and warms up all of the material, all the mass, the biomass particularly in the greenhouse, and this biomass will then re-radiate out infrared energy, which is heat. We feel heat, but it's really a form of light that's being emitted. So in the greenhouse, we have the sunlight coming in through our atmosphere, like the glass in a greenhouse. The UV light is absorbed into the surface of our planet, whether it be the oceans or the continents. And then those will re-radiate infrared energy back out towards outer space. And these molecules act like the glass, where it will absorb that infrared energy, that long wavelength energy, and it will re-radiate it back down to the surface. So in a way, it kind of gets caught in here for a while until it eventually makes its way to outer space. So in a way, it's sort of slowing down. There's a lag behind what gets caught and what's actually lost, which is what allows us to have the environmental conditions we do have on this planet that are very hospitable for us to live. So we have shortwave, another way to say it, we have shortwave UV energy coming in, absorbing into the surface of the planet. That planet re-radiates out long wavelength energy, infrared, and it's absorbed by the greenhouse gases, and some is lost to the outer space, and some of it comes back down, bouncing back and forth between this energy transfer exchange until eventually it's lost, while new energy is continually coming in from the sun. So ideally what I'm sort of describing to is an energy budget. So we have our incoming energy, so 100% of this solar radiation comes and passes through, and so some of that comes down, is absorbed into the land. Some of that is reflected out by clouds, some of it's reflected by the surface, some of it's reflected by other aspects of the atmosphere. We also have, in some cases, what was absorbed now re-radiating outwards in the form of long wave energy. So this would be our infrared energy that was absorbed and re-radiated out. This is the UV that's being reflected back out. Okay, so this is not, there isn't an opportunity for this to absorb in. This is just purely being reflected out depending on what variables are present, like just our atmosphere, reflected by clouds, and maybe reflected by smooth and light surfaces. All right, let's skip past this and introduce what temperature lag is. So we're going to go past this independent practice that was for angle of insolation, and we are going to talk about the time lag, the lag behind energy that comes into the planet and what that does over the course of a day and over the course of seasons. So don't get overly caught up with the diagram here. This is here to challenge yourselves if you'd like to. We'll talk more about how the seasons work based on lag on daily and seasonal cycles conceptually. Okay, I don't have any specific questions for this, but let's go through what that means. On a daily cycle, we tend to have a hottest part of the day and a coolest part of the day. That was in the meteorology introductory notes, where I told you a few times, if you want to try to pause, go back to those notes, or pause and try to recall that information, maybe you can stop and jot that here and see if it confirms with the information that's in this graph. Okay, so if we take a look, go ahead and pause if you haven't already done so. Okay, so we're back. Temperature minimum is around 6 a.m. So this here is our temperature line. I'm going to put that in red. This is our temperature line right here. Okay. We see our lowest temperatures around 6. We see our highest temperatures around 2 to 3. Okay. That makes sense. Cool, cool. That makes sense. So then we've also got insolation maximum. So right here, this line that I'm going to put in blue is the angle of the sun during the day. Okay. So that's insolation maximum. So when we hit insolation maximum around noon, you're going to not have your highest temperatures just yet. It's going to take time for that insolation to absorb into the ground. It's going to take time for it to re-radiate into the air through convection to warm up the air. So you're going to have a lag period between when the sun is highest at its angle in the sky and eventually when the warmest temperatures are going to be during the day. Again, because that sun is coming in, that high intensity radiation insolation is coming in, absorbing into the ground. That ground has to heat up, which then causes there to be a heating of the air through convection. And so that's going to take time. And that is the insolation temperature lag on a daily basis. Okay? Now, seasonally, depending on the tilt of our planet, again, the insolation maximum. So I'm going to go with blue to show the insolation line, which is the angle of the sun over the year in blue, and our temperature lag on average over the entire year by month. So we see that in June 21st, just like our daily, June 21st, that's the highest angle of any day of the year. That's the most intensity on our northern hemisphere of the planet. It takes time in terms of days for that whole northern hemisphere to finally absorb enough heat and radiating enough heat into the air to start causing temperatures to be higher about a month, a little more than a month later, towards the end of July, almost beginning of August. So when you hear about those really hot days in August, that's a result of the insolation, that angle of insolation in June into the end of June and maybe even the beginning of July, heating up the whole hemisphere and eventually catching up and giving us our highest temperatures at the end of July, beginning of August. Okay. So with that said, let's go to one more thing. El Nino, La Nina. You may have heard of these before. They don't get as much attention in the news as climate change does, but we do see, or we do even have records, written records, not necessarily the type of records we have nowadays, but about 350 years worth of El Nino, La Nina records showing to us that there are variations in the temperatures of water off the coasts of North and South America, and these bring about different types of planetary climate change conditions during the period of time in which they occur. So one thing to point out, El Nino, La Nina happen every 3 to 7 years. There isn't an exact value with that. But during El Nino, on this left side here, El Nino, we have much warmer than usual waters off the west coast of South America. So places like Colombia and places like Peru and Ecuador, they're going to be maybe experiencing much higher than usual rainfall. So during El Ninos, you tend to hear about a lot of flooding here and landslides. Okay? Now here in the United States, it tends to be cooler than usual, so we don't really get as many storms during El Nino, maybe during the summertime, because since it's a little on the cooler side, there's a little less evaporation, there's less wreck occurring and creating these MTs, so these MTs aren't as dense with moisture. Same thing happens down here when you're in the southern section of Chile and Argentina. They are getting kind of a similar situation where it's not the same. Also, these warmer waters tend to inhibit fish in these areas, and it does affect local economies for these particular countries. In the sense that it's a little on the drier side, that means we tend to see more droughts during El Niños in the United States. The opposite, during a La Nina, which follows up an El Nino, we have a reversal of these temperatures along the coastlines, and you end up having slightly cooler than usual during La Nina in our Central American and Northern South American countries, but we have warmer than usual for us. So these, we tend to have much more moist seasons, meaning especially in wintertime, if we're going into a La Nina in the wintertime, you can definitely expect quite a few winter storms that are packing a serious punch for those nor'easters. So this gives you a broad overview of El Nino and La Nina and climate change. So how about we fast forward ourselves to the climate change guided and independent practice document that you can find in that shared folder. You can access the access points in the access point folder. Did I say access points enough? I think I did. All right, so what I want you to do, I'm going to pretend to pause, but you're actually going to pause, and you're going to give these a shot, and then we're going to come back and review them together. And break. We're back. All right, so we've got 2 questions here. Let's go through them. Most of the infrared radiation given off by Earth's surface is absorbed in Earth's atmosphere by greenhouse gases such as water vapor, carbon dioxide, and your infinite knowledge of earth science, or if you just went back in the notes, you may see that the last one would be methane. And in the UK, it's methane. No problem. But you understand, so CH4, it's always good to kind of remind yourselves what those chemical molecules are, because you never know if they're just going to throw that at you. All right, let's go on. Number 2, figure 1. And our question is down here. All right, base your answer to this question on the data table below and on your infinite knowledge of earth science. The data table shows how the destruction of the ozone layer in Earth's atmosphere has affected the amount of UV or ultraviolet radiation reaching Earth's surface beneath the areas of ozone destruction. So let's take a look at the chart. We've got ozone loss and ultraviolet radiation here. We've got our left column titled ozone destruction percentage. We've got 0, 15, 10, 15. It looks like we're counting it by 5s. Okay? Over here, average increase in ultraviolet radiation reaching Earth's surface by percent. So we have ozone destruction, so how much of it is destroyed, and then we have how much more UV radiation is making it to the surface. So if we look here, we've got percent of destruction, so the hole is getting bigger in this case, and because of the hole getting bigger, more is reaching the surface of Earth. Just something you want to start to develop is that idea of building the relationship between the data as we're reading it. All right, so refer to figure 1. We did that. Question: ozone closer to Earth's surface has been identified as a greenhouse gas. Identify 2 other gases in Earth's atmosphere that are considered major greenhouse gases. Well, if ozone is considered one, we can go back to thinking about the ones we have. So we have water vapor, we have methane, and carbon, not carbon, carbon dioxide. That's dioxide. Turns out, for this question associated with this chart, we didn't need the chart. But as I've explained to you in the past, Regents questions tend to have a couple of questions lined up based on a chart or a diagram or a picture. So in this particular case, the way this question sorted out was this was just for us to talk about greenhouse gases, and maybe this question asked you to develop that relationship in a sentence form in another question. So right now, what I'd like you to do, pause the video, or just continue on your own using your access points, your answer keys, complete the independent practice. If you have any questions, as always, shoot them down underneath in the comments. I'll try to get back to you as soon as I can. Google Classroom, keep up with Google Classroom. We'll be on WebEx if you got questions. And beyond that, we'll see you tomorrow.